Good afternoon, everyone. It's my great pleasure to present our guest, Professor William Simpson from the University of Cambridge. First and foremost, I must say that Professor Simpson is one of the winners of the fourth edition of the Expanded Reason Awards with a work in the research category, What's the Matter Toward a Neo-Aristotelian Ontology of Nature. William Simpson is a junior research fellow of Wolfson College, and honorary research fellow of the University of St. Andrews. He's a research associate of the Divinity Faculty in Cambridge and a research associate of the Ian Ramsey Center in Oxford. His current work on the philosophy and theology of nature is part of the international project God and the Book of Nature. Please welcome Professor Simpson with a big round of virtual applause.
Thank you very much. Thank you. What is the world made of, and how do we fit into it? If it is made out of something, then are there many things, or is there really just one thing from which everything else is derivative? These are some of the big questions I'd like to think about in the course of this lecture. But first, I'd like to begin by thanking the organizers for the invitation to speak at this conference. I was delighted to receive an Expanded Reason Award for my work, although I recognize that I'm standing among more senior scholars who are much better established in their fields, and anything I have to share may seem somewhat nascent in comparison. I've been asked to offer both a brief synopsis of my work and a biographical sketch of the intellectual contours that led me to engage in expanded reason type questions. My project concerns the ontology of nature, specifically how the world might be if something like the laws of quantum mechanics are true. It makes use of a working knowledge of quantum mechanics, but it is a philosophical project at heart. I got into philosophy because I wanted to do theology. Could I trust a theologian who hadn't done any philosophy to explain God's relation to nature? I got into physics because I wanted to do philosophy. Could I trust a philosopher who hadn't done any physics to correctly interpret what physics says about the world? But why this concern with relating natural and theological domains of discourse in the first place? I think those of us who share such concerns are typically buying into a success story in which the sciences are successful at generating knowledge about nature. We want to affirm that knowledge, whatever it might be. And we're aiming at a unified picture of reality, which integrates natural and philosophical knowledge. Like the philosopher Wilfrid Sellars, we want to know how everything hangs together. My recent work has been motivated by a conviction that in order to tackle big questions about our place in the world and the relationship between theology and the natural sciences, we need to consider the background concept of nature that is shaping the landscape of this discussion. Because it isn't obvious anymore what this background concept should be. In fact, two major schools in contemporary philosophy of science are vying for our allegiance, which tell different success stories about the kind of knowledge the sciences are generating and diverge in their views on the unity of nature. On the one hand, there's what I call the Lewis and Quinean school of philosophy associated with the philosophers David Lewis and Willard Quine, which conceives success in the sciences in terms of the discovery of universal laws that summarize empirical facts in a powerful and predictively useful way. It emphasizes the unity of the physical world and the universality of scientific truths, offering a physics-centered story about nature which dominated the philosophy of the last century, but has been criticized for being disconnected from scientific practices. On the other hand, there's the Stanford School in philosophy of science associated with the philosophers Nancy Cartwright, Hassek Chang, John Dupre, which offers a different conception of the successfulness of the sciences. For Cartwright, a science is successful at isolating the causal capacities of different entities in nature. It emphasizes the plurality or disunity of nature and the context dependence of scientific truths. To have an informed conversation about the big questions that still matter to many people, I think we need to engage more with scientific practices and reflect again upon the metaphysical underpinnings of the sciences, because the landscape of this discussion is changing. There are three parts to the rest of my talk, involving three institutions of which I've had the privilege to be a part, and three big pictures of the world that give different answers to my big questions about what the world is made of and how we fit into it. The three institutions that feature in my story are the University of St. Andrews, where I learned some physics, the Weizmann Institute of Science, where I put some of my physics into practice, and Cambridge, where I transitioned to philosophy and began reflecting in a more disciplined way upon physical theory and practice. The three big pictures which I have engaged are microphysicalism, in which the natural world is composed of microscopic entities, cosmic monism, in which there is only one fundamental entity, namely the cosmos itself, and holomorphism, in which the natural world consists of different fundamental entities that exist at a variety of physical scales. My story begins in St. Andrews, where I became better acquainted with the standard background conception of nature that shaped the mainstream analytic philosophy of the last century, and where I came into contact with some of the challenges this picture faces from contemporary physics. St. Andrews is Scotland's oldest and most traditional university. Unlike many more modern universities, it is not arranged on a campus, but is distributed over a pretty coastal town. I began taking courses in the physics and philosophy departments, located on separate sides of the town, and became acquainted with two great thinkers who played a significant role in modern philosophy. For David Hume, one of the great Scottish philosophers of the Enlightenment, the world was just one little thing and then another, without any necessary connections between them. David Lewis, a leading philosopher of the last century, offered a formalization of Hume's thinking that he believed to be suitable for expressing the truths of our best physics. According to Lewis, once you've got the microscopic entities or properties in the right spatio-temporal relations, you've got all the chemical and biological things as well. More precisely, the whole truth about the world is said to supervene upon a spatio-temporal arrangement of microphysical properties. Let's consider my questions in the light of this background picture of nature. First, what is the world made of, or what are our best sciences telling us about? In the end, on the standard view, it's all about the properties of particles or fields, that is, the microscopic constituents characterized by our best physics, which simply exist without further explanation. The ultimate story is told by physics, and there's no deeper level than that. But how do we know this is the right way to think about nature? In a word, reductionism. Physics, we are told, has been successful at reducing everything that happens to instantiations of the same set of physical laws, and these laws refer to these microscopic constituents. That gives us some reason to believe this is the right way of thinking about nature. It's the Lewis and Quinian story about the success of our best physics. So where do we fit into this picture of nature as beings who search for meaning and order? For analytic philosophers, the question has been framed in this way. When God made the physical world, did he have to add anything in order for there to be minds or people or life? The landscape of discussion, which was shaped by the standard background picture of nature, is marked by some familiar signposts that might be plotted on a single line. On the right, some kind of materialism or physicalism. Reality is just the material world, and physics has pride of place in telling us the truth about nature. That's what David Lewis thought. On the left, some kind of idealism. Reality is ultimately just ideas in the mind of God. And theology has pride of place in telling us the truth about nature. Thus spake the idealist philosopher George Berkeley. In the middle, some kind of Cartesian dualism or property dualism. Reality is both matter and mind, a more diplomatic division of labor in which physics can tell us about matter, only theology about the mind that made it. And of course, there are other views, vitalism, hylozoism, mitigated idealism, and so on and so forth. But for all its diversity, the standard background picture of nature can be characterized in two ways. First, it offers a flat or monistic conception of being. The natural world consists of some set of basic constituents described by our best physics, and those basic constituents admit no further analysis. Anything else is either some arrangement of these constituents or not part of nature. Second, it has a universal conception of how physical laws apply. The distribution of these microscopic properties is causally closed under one set of physical laws, which apply everywhere in the same way for all time. Any top-down influences on where the matter ends up, produced by macroscopic beings such as ourselves, would violate the laws of physics. Under these rules, the aim of the game for philosophers of mind or theologians, or for anybody else whose subject matter is deemed less respectable than physics, is to relate those things that they want to talk about to the fundamental physical facts about matter, without helping themselves, ontologically speaking, to anything more than is strictly necessary. During my first few years at St. Andrews, my studies of philosophy and physics were not well integrated. I was a dualist by day and a materialist by night. I did discover, however, that quantum mechanics does not fit very well with the standard picture of nature. In basic quantum mechanics, the physical state of a system is not represented by a spatiotemporal distribution of physical properties, but by a wave function defined in an abstract high-dimensional space, which is governed by the famous Schrödinger equation. This wave function determines the observables that can be measured in an experiment. Significantly, different wave functions can be combined as quantum entangled superpositions, which make trouble for the micro-reductionism demanded by the standard picture in two ways. First, entanglement gives rise to non-separable systems in which the state of a quantum entangled system cannot be separated or factored into the states of its separate parts. In other words, it appears that the entangled system as a whole has physical properties which are not reducible to the properties of its parts. Secondly, it gives rise to non-local phenomena in which what happens at some point P in space-time depends not only upon what exists within the causal history of this event, but also upon what exists at points causally separated from P by what is called a space-like interval. In other words, it appears that two things which are not causally connected by any physical mechanism can still influence one another. For example, in the famous EPR experiment involving two quantum entangled particles emitted from a common source, one particle is measured to be spin up when another is measured simultaneously to be spin down, and vice versa, however far apart the two particles are separated. Whilst the two measuring devices in this example have been both set up to register vertical spin, that is spin up or spin down, the polarization angles of these devices can be adjusted separately to create a range of experimental outcomes. Significantly, quantum mechanics predicts that the statistics for this experiment will depend on the relative angle between them, something that neither particle, considered separately, is in a position to know. The physicist John Bell is generally accepted to have shown that the measurement outcomes of the EPR experiment cannot be accounted for by assuming that each particle carries properties as local observables of the system, which are available to be measured separately all along. In other words, it seems we cannot infer the existence of any intrinsic properties possessed by a microscopic particle on the basis of a quantum measurement of a system's local observables. To give you an illustration, the quantum world looks rather more like an anthill with its labyrinth of interconnections than a mosaic put together from one little piece and then another. There is now a vast literature trying to revise the standard conception of nature to fit quantum mechanics, and an increasing number of philosophers who are coming to reject that picture. The second chapter of my story takes place in the Weizmann Institute of Science, where I began applying quantum physics to some real problems in the Department for the Physics of Complex Systems, and where the disconnect between the idealized conception of physics that cosmic monists believe and the way physical theory is used to explain things in practice became somewhat clearer to me. The Weizmann Institute is a research institute in Israel in the town of Rehovot, just south of Tel Aviv. I did most of my doctoral work in physics there and lived for some time just outside the walls of the institute on a street called Baruch Spinoza. According to Spinoza, the great Jewish philosopher of the early Enlightenment, the world was just one big thing, a single substance, of which everything else was a mode or modification. Jonathan Schaffer, a leading philosopher of this century, has revived something like Spinoza's conception of nature, arguing on the basis of quantum entanglement that whilst there are many things in the world, they are all metaphysically grounded in the one thing, the physical cosmos. Schaffer's physics-based argument might be reconstructed as follows. Quantum entangled systems which evolve according to quantum laws are fundamental physical wholes. The cosmos is a quantum entangled system which evolves according to quantum mechanical laws. Therefore, the cosmos is a fundamental physical whole. Schaffer assumes it is possible to model the whole world as a single quantum system characterized by a universal wave function, which evolves unitarily according to the Schrödinger equation. Something hotly disputed, incidentally, since the wave function seems to be subject to some kind of localization or collapse, and many physicists have taken this collapse to be an irreducible fact. Let's apply my earlier questions to this revised picture of nature. First, what is the world made of, or what are the fundamental things our sciences are telling us about? In this case, they're telling us about things which ontologically depend upon the cosmos as a whole, a single substance which exists without further explanation. There's no deeper level than that. But this is no longer a flat picture of reality. Now there's a metaphysical story to be told about the structure of the cosmos, which supports different levels of being. Philosophers are back in business. But where do we fit into this picture of nature? Well, human realities are still on the back foot. Whilst microphysicalism placed fundamental reality on the microscopic scale, cosmic monism places it on the cosmic scale. Macroscopic intermediate scale entities like you and me don't get much of a look in. And Cartesian dualism is now looking stranger than ever as a way of avoiding materialism. Each soul would be competing over the same substance. Psychic holism or perhaps panpsychism might be a better fit. Finally, how do we know these facts about nature? Again, reductionism. Physics is supposedly successful at reducing what happens in the world to instantiations of physical laws, only the laws happen to be quantum laws, and everything is quantum entangled. This is still the Lewis and Quinian story about the success of our best physics. But quantum mechanics also makes trouble for this more holistic picture of nature, which still assumes that the world admits a unique microphysical representation and which still rules out any top-down influences from macroscopic systems on where the matter ends up. In my doctoral work at the Weizmann, under the supervision of Ulf Leonhardt, I was applying quantum mechanics to forces which emerge between macroscopic bodies due to quantum fluctuations in their materials. You can find these sticky quantum forces throughout nature, and you can predict them by applying quantum mechanics judiciously to the electromagnetic field. But there are subtleties in the application of quantum mechanics to real-world problems which are easily overlooked. For example, the chemical bonds between molecules have sometimes been described as being nothing but a sum of van der Waals forces that is too large to compute in practice, but is explicable in principle in terms of microscopic quantum electrodynamics. However, standard textbook expressions of the van der Waals force are highly idealized and depend on assumptions about the macroscopic environment of the system that are not always made explicit. The Casimir-Polder expression for the force between two particles, for instance, assumes the idealized geometry of free space, but a more general expression can be derived for a realistic environment with an arbitrary geometry, for a system in a state of thermodynamic equilibrium, from which the Casimir-Polder expression may be recovered as a limiting case. In reality, the electromagnetic field is not free, but is scattered by materials comprising the surrounding environment. This scattering affects the microforces experienced at each point. In addition to scattering the fields, the surrounding materials serve as a heat sink that absorbs the field, and these materials are characterized by macroscopic thermal properties. As electromagnetic waves propagate throughout these materials, they displace electromagnetic charges, and in so doing, they induce electric currents in the materials. Yet the energy does not flow out of the electromagnetic field and into the materials without coming back again. In fact, the materials heat up due to the current generated by the field, then radiate the energy they have absorbed, thus contributing to the surrounding field. In this environment, the quantum energy levels of microscopic molecules are thus permanently dressed by the thermalized electromagnetic field due to their interaction with their immediate environment. I came to realize that even for the case of quantum fluctuation-induced forces at zero temperature, the so-called ground state of the quantum field remains one in which the macroscopic thermal properties of the materials and the microscopic electromagnetic properties of the fields are inextricably coupled. In other words, our best description of any of the forces that we can measure is one in which macroscopic features of the system are implicated. These are situations that cannot be represented in terms of the wave function of a microscopic particle configuration. In fact, the heat sink in the materials can only be modeled by a continuum of oscillators with infinite degrees of freedom. And quantum systems with infinite degrees of freedom do not admit of unique microphysical representations. To accomplish a microscopic reduction, we would have to demonstrate how to remove these background features by showing that macroscopic properties like temperature can be represented within a finite quantum mechanical model that admits a unique microphysical representation. But there are plenty of examples in physics where quantum mechanics is applied to phenomena that do not admit a unique representation, such as phase transitions or the Unruh effect. In fact, we have to use physically inequivalent representations in order to capture all the changes in their behavior. In short, it seems that quantum laws do not apply in exactly the same way to everything as philosophers often suppose. To pick only one representation of quantum mechanics as the true representation of the cosmos would be like claiming the whole of Tchaikovsky's first piano concerto can be played using the chord C major. The third chapter of my story takes place in Cambridge, where I began reflecting more deeply on physical theory and practice and pulling some of these philosophical reflections together. I was granted a scholarship to pursue a doctorate in philosophy at Peterhouse, the oldest and quirkiest of the Cambridge colleges, under the supervision of Hasek Chang and John Maranbon. In this part of my talk, I will offer a brief, non-technical and selective synopsis of my thesis. My thesis is concerned with the ontology of quantum mechanics. Its object is to put forward a general account of the structure of nature and an inventory of what exists in the world if the laws of quantum mechanics or a theory like quantum mechanics are true. I was concerned, however, with producing an account of nature that can explain how scientific inquiry is possible, which pays attention to the details of scientific practices conducted by rational and embodied human agents. The main argument of my thesis is, first, that the quantum revolution that has taken place within physics requires a radical reimagining of the standard microphysicalist forms of metaphysics that dominated analytic philosophy in the last century, in order to accommodate phenomena like quantum entanglement. Secondly, that when we take seriously the emergence of macroscopic properties in physics and the diverse kinds of empirical content captured by quantum theories, this reimagining is further constrained to take something more like the holomorphic picture of nature held by Aquinas, in which the world contains substances that are metaphysically composed of matter and form. It is now a truism among philosophers that one cannot simply read off reality from our best physics. Indeed, many interpretations of quantum mechanics have risen, for which philosophers have proposed radically different ontologies. In their quest for intelligibility, all these proposals appeal to something more than the brute empirical facts. According to Everettians, for example, the physical world is continually fragmenting into separate branches. According to Bohmians, for instance, the physical world consists of a single configuration of particles following trajectories which are guided by the wave function. Insofar as metaphysicians have taken quantum phenomena into consideration, their proposals have typically taken place at a high level of abstraction, without much regard for scientific practices, and have focused on idealized microphysical models without much regard for the context of their application. In my work at Peterhouse, I sought to trailblaze a different approach. In the course of exploring a sequence of models that offer an ontology, each offer an ontology of quantum mechanics, I came to the conviction that the metaphysics of quantum mechanics, which specifies what quantum mechanics is about, should not be rigidly separated from the epistemology of scientific inquiry, which takes into account the ways in which scientists successfully explain phenomena, nor should it be rigidly separated from the anthropology of scientific inquiry, which considers the conditions in which scientists have the possibility of engaging in scientific practices. Nor should we seek to frame a metaphysical model apart from a concern for the deeper meaning of scientific inquiry, embodied in the search for unity and truth. By holding these concerns together, which inform the concept of expanded reason, we can avoid, on the one hand, an implausible reductionism, which emphasizes some truths at the expense of others, or a cynical skepticism, which abandons the truth and the integrity of nature altogether. My thesis, which I'm turning to a series of papers, is divided into 3 parts, in which I discuss Aristotle's doctrine of Holomorphism, in which nature consists of substances with different natures, and how it was replaced by micro-reductionism in the wake of the scientific revolution. Secondly, why there is good reason to think that microphysical reductionism is ultimately incompatible with quantum mechanics. And thirdly, how a more holistic approach to the philosophy of nature may lead us back to some kind of holomorphism, which looks for the unity and integrity of reality at a deeper metaphysical level. In the first part of my thesis, I begin by discussing the doctrine of holomorphism. According to Aristotle, as he has generally been understood, nature does not consist of a monistic arrangement of physical constituents to which everything is reducible, but is carved into a plurality of substances which have different natures. These substances are not governed by universal laws, which summarize how everything just happens to take place, but exercise causal powers which bring about necessary change. But the various powers of these substances only manifest under certain conditions, and a plurality of sciences are necessary in order to uncover the truth about their natures. On the one hand, the old Aristotelian metaphysics resonates with some of the themes of the new Stanford School of Philosophy of Science, especially the philosophy of Nancy Cartwright. On the other, it rejects the fragmentation and cynicism that some philosophers of that school have embraced, seeking the unity and integrity of being at a deeper metaphysical level. Aristotle introduced the metaphysical concepts of matter and form to explain how physical substances are generated and how they take on different characteristics during the course of their existence. Hule, or matter, is that which gets determined. Morphe, or form, is that which determines matter. According to a traditional line of interpretation, often attributed to Aquinas, matter is not a kind of Lego-like stuff which has its own intrinsic physical properties. Matter is potentiality for substance, which is determined by substantial form. Substantial forms, according to Aquinas, are that by which substances are what they are. Both matter and form are required to explain the physical changes we observe in nature. I discussed the rise of microphysicalism in my thesis, which followed in the wake of the scientific revolution. And in this thesis, the properties of complex physical entities are reduced to the properties of their microscopic constituents. I say how I think we got into this mess. And I suggest that the widespread rejection of form in early modern philosophy resulted from the physicalization of the concept of matter, in which the concept of matter required intrinsic physical properties independently of form, combined with the rise of a kind of reductionism, which I later argue contemporary physics does not support. In the second part of my thesis, I explore how the phenomenon of quantum entanglement challenges the standard microphysicalist conception of the world as consisting fundamentally of particles or fields characterized by intrinsic microphysical properties. My object here is to show that the quantum revolution restores the viability of something like Aristotle's conception of substance. I begin by discussing the problem of quantum entanglement and the trouble that this makes for the standard microphysicalist view of the world that we've discussed, in which the whole truth about nature supervenes upon the spatio-temporal arrangement of microphysical properties. I then consider Michael Esfeld's new metaphysical model, superhumanism, which tries to salvage the standard microphysical picture of nature by adopting the Bohmian interpretation of quantum mechanics, which posits a configuration of particles that are guided by the wave function, and by stripping the microscopic constituents that feature in the standard microphysical picture of their intrinsic microphysical properties. Yet Esfeld's recovery operation is really a form of cosmic monism. The microscopic particles that he posits have no natures or identities of their own, but are just nodal points in a giant cosmic network. According to superhumans, the world is made solely of matter points, which have no intrinsic properties, being nothing over and above the distance relations in which they stand. And the laws of nature, including those of quantum mechanics, are Humean laws, which just summarize how these matter points happen to be distributed. I raise many objections to this conception of matter. For example, I argue that particles which stand in symmetric configurations cannot be individuated if their configurations are identical to sets of distance relations. If the Bohmian particle configuration ever became symmetric, according to this model, the whole world would collapse. I also argue that a world of matter points is one in which the laws of nature are radically underdetermined, and that a world that consists solely of distance relations cannot ground the existence of particles that persist through time. You can find some of my criticisms in a paper called What's the Matter with Superhumanism in the British Journal for Philosophy of Science. In short, this picture of the world, though elegantly simple, is simply too sparse to do all the explanatory work that a realist interpretation of a theory like quantum mechanics is supposed to do. It seems something more is needed, besides a distribution of matter without physical properties, in order to account for the truth about nature's laws. During this part of my work, I rekindled the idea of substantial form as that something extra which is needed, in addition to matter, to ground the laws of nature and the properties of physical systems. I introduce a new metaphysical model for the Bohmian interpretation of quantum mechanics, just for the sake of argument, which replaces the matter points with entities I call power atoms, and which enriches the ontology to include what I call a cosmic form. In this model, one configuration of power atoms has the power to necessitate another configuration, while the cosmic form transforms the power atoms into a single substance by continuously endowing them with powers to change their velocities. These powers are not intrinsic to the power atoms, which are caught up within a process that is manifested by the cosmic form. The cosmic form determines the powers of the power atoms at each moment in time, and hence determines their trajectories through space. Yet the cosmic form, which confers these powers, does not exist apart from the power atoms, but unites itself to the particle configuration by being the grounds of their causal powers. This alternative model discards Esfeld's Humean conception of the laws of nature, in which the laws merely summarize where the particles are distributed, in favor of an Aristotelian essentialist conception of laws. According to this model, the law-like behavior of the particles manifests an essential power of the cosmic substance to choreograph the trajectories of its particles through space. This alternative model is able to overcome the various difficulties that I raised to superhumanism by deploying something analogous to the holomorphism of Aristotle, although the concept of matter in this model is not quite the matter of Aristotle, and it posits only one substantial form. You can read more about this model in a forthcoming paper called Cosmic Holomorphism. However, although this model may handle entanglement, it is just another form of cosmic monism. That is the second picture of nature we discussed, inspired by the philosopher Spinoza. This is not the picture I ultimately put forward in my thesis. It does not do justice to the macro-emergent properties we find in the kind of complex systems that I was thinking about at the Weizmann. My goal in the third part of my thesis is to argue that when we take seriously the phenomenon of macro-emergence in physical systems, our reimagining of the metaphysics of nature is further constrained to take the shape of something more like the holomorphism of Aristotle and Aquinas, in which the world contains a plurality of substances at different physical scales. Neither superhumanism nor cosmic holomorphism, I suggest, make a sufficiently radical break with the standard microphysical picture of nature. In fact, since the scientific revolution, a chasm has opened between what Wilfrid Sellars called the scientific image of the world, informed by our best physics, and the manifest image of ordinary experience, which includes scientists and the instruments they manipulate to perform their experiments. This chasm has been widening since, contributing to the sense of disenchantment associated with the modern period. Philosophers have traditionally sought to give accounts of our best scientific theories that can furnish us with the conceptual resources that we need to give a true and complete description of nature. However, such accounts must be consistent with our knowing such theories to be possibly true by means of the kind of empirical knowledge that is gained from conducting experiments. The physicist Abner Shimoni described this constraint as closing the epistemic circle. In pre-quantum physics, as the philosopher Robert Koons points out, this constraint on philosophical theorizing seemed easier to satisfy, and philosophers were more optimistic about the possibility of giving an account of the scientific image from which we could recover the manifest image. First, the psychological states of scientists could be understood in terms of causal roles played by their microphysical parts. Secondly, the macroscopic instruments upon which scientists depend could be identified with aggregates of microscopic particles arranged in three-dimensional space, whilst their thermal and chemical properties were considered to be reducible to the properties of their microscopic parts. The quantum revolution that concerns my thesis, however, seems to have enlarged the gap between the scientific and the manifest image, from the standpoint of the Lewis and Quinian approach to realism, in ways which threaten to undermine the empirical content of our best theories by leaving certain features of the manifest image unexplained. First, the quantal properties of physical systems constitute superpositions of incompatible observable properties which are quantum entangled, such that the state of a system cannot be decomposed into the properties of its microscopic parts. We have seen how this holism is difficult to reconcile with the standard microphysical picture of nature. Secondly, quantum models of simple systems of particles fail even to approximate the thermal and chemical properties of complex macroscopic systems, such as the instruments which scientists depend upon for their experiments, which demand different context-dependent representations, which have infinite degrees of freedom. This pluralism is difficult to reconcile with the cosmic monist picture. The Lewis and Quinian approach to realism seemed so simple and reasonable. Stick in some universal laws and fundamental constituents into the ontological sausage machine, crank the handle, and out pops a set of possible worlds. But alas, when you stick quantum mechanics into the sausage machine, you get baloney. Yet, what is the alternative to cynicism if we are unwilling to hunker down into reductionism? Perhaps our problem is that reason has become too narrow. Let's apply some expanded reason type questions then in relation to the Lewis and Quinian approach to realism to tease out some of its presuppositions. First, as touching the question of meaning, it assumes that if there is any meaning or integrity to reality, it must be found among physical entities that stand without need of explanation. In practice, however, we cannot explain all natural phenomena in terms of a unique microphysical representation. In that case, the search for meaning must go deeper than the material level. Secondly, as touching the epistemological question, it assumes that the truths that successful sciences uncover are universal in scope and unqualified in their application. In practice, however, even our best physics deploys different representations of systems which are context dependent. In that case, we may need a metaphysical account that admits an element of pluralism. Third, as touching the anthropological question, it assumes a passive conception of the scientific inquirer as an individual who observes the regularities which take place in the world. In practice, however, scientists who make observations are active in isolating physical systems from the noise of their surroundings in order to detect conditional law-like behaviors. In that case, we may need a metaphysical account in which macroscopic entities can determine where the matter ends up. Finally, as touching the ethical question, it embodies a perspective in which the ultimate good of scientific inquiry is the acquisition of a body of universal knowledge whereby we can maximize our control of the world. In practice, however, most scientists are concerned with understanding the behavior of local systems in terms of models which only apply under certain conditions. In that case, we may need a metaphysical account in which it is sufficient for the good of science to get to know these local things a bit better. In my thesis, I propose a third metaphysical model, holomorphic power pluralism, which deploys a recent contextual interpretation of quantum mechanics put forward by the physicist-cosmologist George Ellis and the physicist Barbara Drussel. Like other theories of quantum mechanics, this theory allows the wave function to collapse. The world is not a quantum entangled whole. Unlike other collapse theories, these localizations of the wave function depend upon the local macroscopic context of a system. In short, there is a feedback loop from a particle via the intrinsic heat bath of the measuring device back to the particle, which introduces nonlinear terms into the Schrödinger equation. So the microscopic world is not causally closed. In the model I put forward in support of this contextual interpretation, the world is made of what I call thermochemical substances, which have both quantum properties determined by wave functions and classical properties which set the boundary conditions for the temporal development of the wave function. This model is able to accommodate the phenomenon of quantum entanglement, which troubles the standard microphysicalist picture, whilst rejecting the radical holism of cosmic monism. Quantum entangled particles are not separate substances on this picture, but dependent parts of thermochemical substances. This model is able to accommodate the phenomenon of emergence in macroscopic quantum systems without embracing cynicism and fragmentation. Different substances have different substantial forms, which determine their natures and admit different quantum representations. And this model is able to ground the possibility of scientific inquiry within the physical world. Scientists are conceived as individual substances which have causal powers to probe nature. This proposal converges with Robert Kuhn's recent claim that the world consists of thermal substances, although it builds up this model in a slightly different way. From this holomorphic perspective, it is wrong-headed to ask whether God had to make something extra besides the physical world in order for there to be minds, people, or life. There is no flat and monistic set of physical properties which exist without further explanation. When God made the physical world, he made both matter and the forms. In conclusion, the narrow reason which gripped philosophers in the wake of the scientific revolution tried to explain the world in terms of a physicalized sort of matter. Yet the more we have learned from the sciences about nature, the more this conception of matter seems to have slipped through our fingers. In order to enrich the scientific image of the world and recover the forms which endow matter with its physical properties, we shall have to deploy an expanded reason. Thank you for your attention.
Okay. Thank you very much for your compelling and engrossing lecture about the dialogue between philosophy and physics on the main conceptions of nature, Professor Simpson. I find the epistemological research of a metaphysical foundation for this background concept of nature to be not only of great interest for the Expanded Reason Institute, but also quite necessary for the development of any science. Now we have time for some questions and answers in an interview format, if you're so kind. And I will begin with the first question I would like to ask you is, one of your big concerns, big questions, concerns what the world is made of. What are the motivations for a view like superhumanism? How could someone believe that the world is made of nothing but distant relations?
Thank you. Superhumanism is not an unmotivated position. It attempts to give an account of the nature of matter by combining three ideas in contemporary philosophy. First, superhumanism is a form of what's called ontic structural realism. This is the view that what exists fundamentally is structure rather than entities or things which have properties. And there's a background story to this position. Since the late 1990s, many philosophers of science were persuaded by John Worrell that structural realism is the best way to break the tension between the famous no miracles argument for realism and the pessimistic meta-induction argument for anti-realism. According to the no miracles argument for realism, the existence of the entities and properties to which our best physics refers the best way to explain the success of our best theories. However, according to the pessimistic meta-induction argument for anti-realism, all our physical theories have turned out to be false, and so by induction, we have no reason to think the theories we currently venerate truly refer to some set of basic entities or properties which make up reality. And ontic-structural realism, roughly speaking, is the claim that there is some kind of structure, nonetheless, which persists through theory change, even if the entities and properties do not. Mm-hmm. Secondly, superhumanism takes what is called a primitive ontology approach to quantum mechanics. And this is an attempt to account for quantum phenomena in terms of a distribution of matter in three-dimensional space or four-dimensional space-time, such as a particle configuration, and a law of nature that describes its development through time. And Michael Esfeld thinks that the Bohmian version of quantum mechanics can specify that law of nature for the temporal development of this matter, just so long as the nature of this matter is cashed out structurally in terms of distance relations rather than in terms of intrinsic properties. And the third ingredient is what's called a best system account of laws in the philosophy of science. So according to this account, a regularity in nature qualifies as a law of nature, just in case it's an axiom in the best system that balances strength and simplicity in deriving all of the facts. It's a Humean view because there's nothing to explain why one thing follows after another. Hume was very skeptical about the idea of there being any necessary connections in nature or of things having natures that they act out of, which make things happen. So Esfeld thinks of the laws of quantum mechanics or Bohmian mechanics as being the best way of just summarizing how these matter points are distributed. It's a pretty bleak view of reality, and I don't think it ultimately works, but it's been great fun to wrestle with the ideas.
Thank you very much. Now we have a question from David Bere. I will try to translate it from Spanish. Nowadays, there is a lot of talk about the relationship between quantum mechanics and theology. Specifically, quantum mechanics, as it is usually explained or exposed, is it a reality that, or a conception that serves as kind of a bridge between visible matter and invisible matter? And that's, I don't know if I've expressed myself.
Is what supposed to be the bridge, sorry?
Between, if we can understand quantum mechanics as a theory that explains or is kind of a bridge between visible matter or the physics about visible matter and invisible matter. Or visible matter and invisible reality. Sorry. And
something beyond the visible. If I understand the question, I'm not quite sure what the link was to theology, but the kind of account that I'm seeking to put forward, this holomorphic account, which is matter and form, is a non-materialist account. There's certainly more materiality than the material properties. There are, on this view, forms which inform matter. So that sort of takes you to a deeper level of analysis than just pure physicalism. Physicalism being, if you like, one of the main rivals for a theist who wants to say that there's more to reality than just the physical world. So there's nothing explicitly theological about the account that I'm giving, but it does take you beyond matter, certainly beyond the visible world. And it commits you to more than that. I hope that's a reasonably helpful answer.
Yes, I think it is. Thank you. My second question, another of your big questions concerns how we fit into the world. Could you say more about why you found the materialist view of the reality, which reduces everything to matter, and the Cartesian view of reality, which divides reality into matter and mind, unsatisfactory ways of thinking about how we fit into the world?
Well, if you're advancing materialism on scientific grounds, the key question I'd like to put you is, what's the matter? The title of my lecture. What's everything supposed to be reducible to in the final analysis? Because I'm not sure that there's any satisfactory characterization of the fundamental constituents which can do all the explanatory work that's needed. In the lecture, I observed that there does not seem to be a single representation of quantum mechanics that can capitalize on all of the explanatory virtues of this very successful theory. We seem to need different tools for different jobs. Once we strip away all of the intrinsic and determinate characterizations which materialists have often assigned to the fundamental physical constituents, in search of some lowest common denominator characterization that can be applied universally to matter, there just doesn't seem to be very much left to do the explanatory work that we need doing. It seems you only get a completely materialist reading at the price of explanatory power. But if the explanatory power of a theory is the reason we're supposed to be realists about it, that's a bit of a problem for realists or materialists. As for Cartesian dualism, traditionally, it's relied upon a more determinate characterization of matter than I've espoused in this lecture. Descartes divided the world into the res extensa, the extended or dimensive things, and the res cogitantes, the thinking things. The Cartesian thinks something extra is needed to explain the properties of human beings, but is traditionally a reductionist about a lot of other things, such as the properties of plants and animals. So the same question pops up again, what's the matter? The Holomorphist, by contrast, thinks that nothing in the world can be explained solely in terms of matter, but that every intelligible thing has a form which determines its matter. So the question is, the more pertinent question is, what are the forms, or perhaps what kind of substances are there? I think we have a better chance of answering that sort of question, albeit very fallibly and imperfectly, since there's always more to be known about the things we investigate. One way of distinguishing a Cartesian conception of the human person from a holomorphic conception of the human person is to ask the question, is the fundamental relation between soul and body one of formal or efficient causation? For Cartesian dualists, it has to be one of efficient causation because of their conception of matter. Cartesians are interactionists. Matter has a determined character of its own, so they must posit direct and fundamental causal ties running from mind to body and body to mind. Whereas for holomorphists, by contrast, the causal powers of a material body are grounded, or at least partially grounded, in the essential and accidental properties of the soul, the human form.
Thank you very much. You also mentioned the Bohmian interpretation of quantum mechanics and the contextual interpretation of quantum mechanics. Why do we have all these different interpretations, and how we can choose between them?
The source of this diversity is the so-called measurement problem, which is an open problem in the interpretation of quantum mechanics, because of the role that macroscopic measurements appear to play in modifying microscopic behavior. So it's a little technical, but I will give this a shot. So the fundamental mathematical object within quantum theory is the wave function, as I mentioned in the lecture, or more properly, the quantum state of a system. This object represents the probability of a system having a particular configuration. And standard quantum mechanics tells us that prior to any measurement of the system, the wave function evolves according to the Schrödinger equation. So we know how to start from a given quantum state of a system and evolve the probability amplitudes for all the possible configurations that a system may have in time. But suppose we perform what's called a non-demolition measurement of the system. For example, we try to find out, we try and get a value for the number of photons in an electromagnetic wave. The measurement outcome of our experiment, after this measurement, we know more about the state of the system than the information contained in the wave function. We have ruled out with certainty some of the states to which the wave function assigns a non-zero probability. So to obtain the correct results for future experiments, we have to update the wave function with the knowledge we've gained from our experiment. And this updating is not something that's performed automatically by the time evolution, which is governed by the Schrödinger equation. This discontinuous change is known as the collapse of the wave function, and it's necessary to properly account for the determinate outcomes of our experiments. There's no agreed understanding of this process. Even if something called decoherence is taken into account, the evolution must be supplemented with a discontinuous change of state. According to the physicist John Bell, any realist approach to quantum mechanics that seeks to explain the existence of determinate measurement outcomes, such as the number of photons in the electromagnetic field, comes face to face with a certain dilemma. Either the dynamics of standard quantum mechanics is wrong, and the wave function evolves according to a non-linear Schrödinger equation, which permits the wave function to collapse, or standard quantum mechanics is not complete, and there are hidden variables, or in addition to the wave function, that evolve according to some dynamics of their own. The philosopher Tim Maudlin has argued that in the end, the choice comes down to two possibilities. Either we have to adopt something like what's called the GRW collapse theory, or something like the theory of Bohmian mechanics, which Michael Esfeld adopts. The GRW theory seizes the first horn of Bell's dilemma, the collapse alternative, by incorporating a mechanism which produces random hits on the wave function. And these hits occur universally for microscopic particles, regardless of their context, and result in objective collapses of the wave function. Whereas Bohmian mechanics seizes the second horn of Bell's dilemma by positing a configuration of particles over and above the wave function whose trajectories are governed, are choreographed by the wave function. The guiding equation for these particles depends in a non-linear way upon the wave function, which still evolves according to the standard Schrödinger equation and doesn't collapse. There's a sense in which the contextual model proposed by George Ellis and Barbara Drussel, which I referred to in my lecture, splits Maudlin's choices, his dilemma, by incorporating both a collapse mechanism and by introducing classical macroscopic variables which play a role in contextualizing the collapse mechanism. I shan't say anything much more about this because it does get rather technical. I'll just say that I prefer this model for two reasons. First, it does not introduce any extra ad hoc parameters. The moves which it makes can be accounted for, justified, I think, in terms of thermodynamics and solid state physics. And secondly, it's compatible with a picture of nature in which there are different things in the world which have intrinsic properties. It doesn't seem to require any major revisionary picture of the world. So I think some philosophical judgment is needed to settle upon the right physical interpretation of quantum mechanics.
Thank you very much. We have a question from David Humberto Urdaneta, and the question is, do you think your thesis would help to explain theological phenomena such as miracles? Having in mind, for example, that in Thomas Aquinas' system of thought, they are perfectly plausible.
I'd like to think so, yes. I think the crucial issue here is what I'm pushing against is this idea that there is a microscopic world that is causally closed under one set of laws. I think the picture of nature that comes out of this more holomorphic approach is of a causally open nature in which there are forms of top-down causation. and the various ways in which you might think of God acting in the world as a top-down cause. And I think it certainly opens the way to that sort of thinking. And perhaps the question has a rather a different conception of how miracles come about. But I think that's the key thought, that it's a more open conception of nature. The world is not just deterministically evolving according to one set of laws. There's actually open to many different pathways.
Okay, I have two more questions. The first one, to what extent do you think a philosophical or theological perspective enriches physics? Is a philosophical interpretation of the kind you put forward just a matter of the general overlook or personal worldview of each scientist? Or do you think that physics needs somehow philosophy in some sense? Is one kind of philosophy rather than another a better fit with the scientific method?
So let me begin with the second part of your question first. Is one kind of philosophy rather than another a better fit with the scientific method? I think the answer is yes, although I'd rather frame the question in terms of scientific practices. At the beginning of the lecture, I highlighted a contrast between the Lewis and Quinian school of philosophy and the Stanford School in the philosophy of science, as represented by people like Nancy Cartwright. The Stanford School, for all its diversity, is united by a strong regard for scientific practices as embodied in our best examples of scientific discoveries. And people like Cartwright take the attitude that scientific inquiry delivers real knowledge about the world, and that studying these practices is a good guide to understanding how that knowledge about nature has been gained. The important point here, I think, is that a Cartwrightian approach is not something conducted in lofty abstraction from the world of inquiry, in which experimentalists perform their experiments, but it is concerned rather with how successful sciences achieve the successes that they do, and what sort of epistemological and metaphysical presuppositions are needed in order to understand that success. When one's philosophical project is framed in this way, when the metaphysics is continuous with an empirical inquiry about the world that begins from that sort of starting point, then I think certain skeptical attitudes which characterized the more lofty empiricism of the Lewis and Quinian approach, or the positivistic empiricism of Comte and Laplace, can be set to one side. They're merely logical possibilities that we need not take too seriously. Of course, there are things with natures which we can know about. Of course, scientists can manipulate them and discover their causal powers. The fundamental roles played by knowledge and causation within the context of a scientific practice are undeniable. And a metaphysics that is continuous then with scientific inquiry does not begin with an attitude of skepticism, but rather of affirmation. So I'd say there's a big difference between a philosophy that tries to defeat a skeptic about knowledge or causation by finding some indubitable foundation for that knowledge, a view over God's shoulder, if you like, and a philosophy that embraces our fallibility but avoids giving a hostage to the skeptic. If you say to me that because you cannot find any foundation for thinking that nature contains necessary connections, it would be better to think the world is just one little thing after another, then I think you immediately make yourself vulnerable to a range of skeptical attacks on science itself. So yes, to that second part of your question, I do think that the more Aristotelian approach of Nancy Cartwright is a better fit with scientific practices than the more Humean views which dominated the landscape of analytic philosophy of the last century. But you also asked, does physics need philosophy? Sort of quite an open question. So there's a sense in which I think one can't help having a philosophy. If you don't think carefully about your philosophy, you'll end up believing somebody else's, and it won't be very coherent. I remember C.S. Lewis once said, good philosophy must exist because bad philosophy needs to be answered, something like that. Bad philosophy can get in the way of good practices. If you think reality is unstable, probably won't be able to navigate your way through life very successfully or perform an experiment. But where philosophy really seems to matter to physics, I think, is when you take a step back from the little bit of reality that you're interested in and attempt to make sense of what it is that you're doing and try to fit your understanding into a much larger picture. It's then that I think philosophy becomes indispensable to physics in at least three ways. First, there's the matter of the presuppositions of scientific inquiry. You know, it's not just any world in which we could be engaged in scientific experiments, which we could find out about nature. And in attempting to articulate what some physical theory says about the world, like quantum mechanics, physicists are deploying background concepts that the theory itself presupposes but does not explain. So, for example, quantum mechanics presupposes that the quantal properties of a physical system have the potential to change in accordance with the Schrödinger equation. It does not provide an account of change, nor does it explain whether this law, which governs the way the system evolves, whether it evolves necessarily in this way or only contingently in this way. Those are philosophical questions. Secondly, there's a matter of settling upon the interpretation of a physical theory, which we've already touched upon earlier, previous answer to a question. There's such a matter because our interpretation is often underdetermined by the empirical facts. You know, we talked about different physical interpretations of quantum mechanics. It's not clear what physical theory like quantum mechanics is in fact asserting about the world solely on the basis of its own formalism. The physical meaning of the superposition principle, for example, which permits quantum states to be simultaneously combined, is only settled by adopting an interpretation of which the scope of its application is fixed. You had to be a very naive sort of physicist to claim to be able to read off the ontology of quantum mechanics from the formalism of quantum mechanics without going into the messy business of giving an account of how determinate measurement outcomes are obtained in experiments. So the problem with ignoring philosophy at this level is that there are a number of empirically equivalent interpretations of quantum mechanics for all practical purposes. So we have to find other grounds, other rational grounds for adjudicating between these different views. And I want to suggest a third way in which philosophy contributes to physics, which is at the level, I suppose, of the big picture of the world and how we fit into it. So if you think, as I do, that physics is just not as unified as some science buffs and philosophers seem to think, then there's more philosophical work to be done there. Scientists are interested in measuring a variety of phenomena that emerge at different physical scales. And we've got good reason to doubt that all these properties which emerge at higher scales are just reducible straightforwardly to a set of microphysical properties. And so we have to give some kind of account of how it's all going to fit together and how we're going to do that in a way that we fit into the picture too. So in short, I think physics needs a philosophy of nature. There's incompleteness there at several levels.
So we go to the next question. In your conclusions, you state that in practice, even our best physics deploys different representations of systems which are context dependent. In that case, we may need a model that admits an element of pluralism, end quotation. You have also established that neither superhumanism nor cosmic holomorphism make a sufficiently radical break with the standard microphysical picture of nature, end quote. What do you think should be the fundamental principles for a new epistemological model that could be compatible with the quantum revolution you talk about in your thesis?
I'm not sure I want to put forward a new epistemological model as such. I perceive the quantum revolution in physics as making trouble for certain philosophical departures from the tradition of empirical inquiry that I associate with Aristotle, which is characterized by certain confidence in common sense and the capacity of humans to uncover truths about natures, and has, I think, a strong empirical side to it. According to Aristotle, there are principles of intelligibility, the forms, if you like, which are immanent within the natural order, rather than located in a Platonic realm beyond it, which we can only access by some kind of recollection. And we come to grasp these forms by means of sensory experience as we causally interact with the substances that they inform. So from my perspective, I think it's reasonable to consider Aristotle as a kind of proto-scientist who inaugurated an empirical tradition of scientific inquiry. And to think of something like the Lewis and Quinian approach as a kind of rival tradition, or even a kind of heresy, which offers a revisionary picture of nature that tries to capitalize on the success of our best sciences, but actually misdescribes those practices in some important ways, and ultimately leads us to various forms of skepticism. So I'm not sure I have a very complete answer to your question at this stage, but if you're asking for some guiding principles, then perhaps I can suggest one or two. I think we need something like a principle of charity or credulity. The beliefs of ordinary people about the macroscopic world, about the reality of things which change and which cause other things to change, should be taken seriously. It's not that we can't or shouldn't have our beliefs challenged or corrected, but the sense in which we should assume such beliefs to be innocent until proven guilty. We need a very good reason to reject the existence of change or causality. I find myself tempted to put up a sign on my door that says, "Don't feed the skeptic." And I think we need some kind of principle of common sense. The philosopher Kit Fine recently, very prominent metaphysician, described himself as being of the opinion that real progress in philosophy only comes from taking common sense seriously. I think he said elsewhere that a departure from common sense is usually an indication that a mistake has been made. So I think that we should take the beliefs of ordinary people about causation and change seriously, and that a metaphysics which is guided by our best scientific practices is one which will do so. We seem to live in a world in which we both bring about change and in which change is imposed upon us by things other than ourselves. And I think one gets at the causal powers by asking questions about the causes of all these changes and by conducting experiments in which we can isolate these different causes. But the world does not seem to be made of one set of things which persist through all kinds of change, some fundamental set of physical constituents that are responsible for everything that happens, but rather of things which are generated at some point in time and destroyed sometime later. And I think one gets at matter and form by seeking the principles of that sort of change. So I think I see what I'm doing is trying to, in some ways, vindicate an existing tradition. I'm trying to say that it inherits the explanatory successes of our best sciences and can make good sense of them, rather than trying to come up with a new epistemological model, or saying that the quantum revolution requires us to radically change how we're thinking about everything. It rather requires a kind of a system restore, rather a correction. It requires us to let go of certain deviations.
Thank you very much, Professor Simpson. We have one more very interesting question, but we are out of time. So thank you very much for joining us this afternoon. It has been really a pleasure having you with us. Congratulations for winning the Expanded Reason Award. And rest assured that we will keep an eye on your publications from now on.
Thank you very much.